9.4 is looking at voltaic cells, or essentially what makes up a battery or electrical cell. So what voltaic cells look at, or what they work with, are spontaneous redox reactions that can be organized to generate an electric current. So it's using spontaneity in order to produce electricity. In order to understand if the reaction is going to be spontaneous, we need to understand the reactivity series that was discussed in 9.3 to know which are the proper elements to put together and in which direction the spontaneity is going to move in that reaction. And essentially what they're doing, or what these cells are doing, is instead of just losing heat during the reaction, you're taking that heat and turning it into an electrical current. In order to make a voltaic cell, what occurs is the separation of the two half reactions into what are called half cells. This allows the electrons to flow through an external circuit, isolating only the electrical current and nothing else that may be going on during the reaction, such as a precipitate, heat loss, anything along those lines. These half cells could be named an electrochemical cell, a galvanic cell, or voltaic cell. Voltaic is the most common. These half reactions are what generate electrode potentials. So the electrode is your anode and or cathode in a particular battery, essentially, and the half reactions are the ones that are going to generate the negative and positive charges that is created through the reaction. So a simple voltaic cell looks like this. You are going to have a metal strip submerged within a ionic solution of the same strip. So here we have a zinc strip, and we have it submerged within a zinc sulfate solution. As you can see, then we have our solid zinc, and within that, so we have our solid zinc, and then we have our aqueous zinc ion that is in the solution just floating around. So we have our little zincs in solution. And as those zincs are within the solution, the zinc strip will also become negatively charged as those zinc ions are moving to and from this equilibrium reaction. So if you look at this equilibrium reaction, we have our zinc ions, and then we have electrons floating around, and those electrons find those zinc ions, and they get deposited on the zinc strip, so on and so forth. So it's an equilibrium reaction moving to and from the solid and aqueous state. The zinc ion with its associated electrons, this is what generates what we call the electrode potential. And that is the potential to create the energy or electricity in which we're going to capture. The equilibrium, so the position of the equilibrium determines the size of the potential, how much voltage we're going to get through that reaction, and it depends on the reactivity of the metal that we are using, and that's where the reactivity series comes into play. So we need to be able to identify and know our reactive metals and the position in which it's going to be ionized because of that. So when we are choosing two cells in which to work together, we need to know which one's going to be oxidizing, which one's going to be reducing based on their reactivity series from 9.3. So here is a diagram of two half cells, one that has zinc and one that has copper. Each are individually submerged within their own ion solution. So the zinc is in its zinc sulfate solution, the copper is in its copper sulfate or copper nitrate solution, so on and so forth. So those metals are submerged within those. Now, because right now they're just two individual half cells. Looking at the zinc one, just as discussed before, we have this equilibrium reaction taking place where we have zinc ions residing within the solution, and then we have those two electrons, and then we have our zinc metal. So some of the zinc atoms from the metal release those electrons to the solution, so on and so forth. And that's going to create a negative charge on the metal strip. So I'm going to go through and put in that negative charge just to represent. Because zinc is a more reactive metal than copper, it is going to be the one that wants to oxidize, will be more readily oxidized, and therefore it's going to be losing its electrons. And after you see the finished setup, it'll make a little bit more sense. Then copper, looking at copper, we have copper 2 plus, that's its ion with its 2 electrons, and the solid copper metal that we have there. So some copper ions in the solution accept electrons from the copper rod, and that creates a positive charge on that copper rod right there, or copper strip. And this is understanding in which direction is favored based on the reactivity of the element. Because zinc prefers to be oxidized over in the zinc solution, that strip becomes negative because it is releasing electrons to the solution, and then copper prefers to be in its solid state. It has a very low reactivity, therefore it easily will give off electrons to the solutions, so on and so forth. Now, what needs to happen now is we need to connect the two cells. So the more reactive metal is going to have the more negatives in its electrode potential. And I'll discuss that in a minute. All right. So now we need to connect our two cells together. So we're going to put a wire connecting the two. It's an external wire. Attached to it, just so what we know what's going on, we're going to attach a voltmeter. And this voltmeter is going to read the amount of energy or electricity moving through. So our electrons are going to move through, and it's going to be read by our voltmeter. When we are setting these up and to know whether to expect positive voltage, negative voltage, volume of voltage, whatever it happens to be, we need to be able to determine which electrodes belong to which element. Electrodes are essentially identifying where the electrons are going. We have our anode. Anode means negative, so it's the negative side. The anode is always where oxidation occurs. So the element that is more readily oxidized or is the stronger reducing agent is going to be your anode. The opposite side is going to be your cathode. So cathode is where the positive side is, and that is going to be where reduction occurs because it wants to gain the electrons that are being lost from the oxidation side of the cell. That being said, in the solutions by themselves, we have equilibrium reactions going between the ions and the solid metals. But when we attach that external wire, and essentially we are completing a circuit and we're allowing a circuit to move, that is when we create the true half reactions. So this is where we now are identifying that zinc prefers to be oxidized, therefore it's leaving its equilibrium state, and we are going from our solid zinc to our ion zinc, releasing electrons. Those electrons are going to move across that wire through the voltmeter, so we know how much is there, to the copper metal. Because the copper metal prefers to be reduced, or is essentially forced to be reduced because of its position in the reactivity series, that copper ion is going to accept those electrons to create a solid copper precipitate. And so we will actually see the copper ions within that solution precipitate out. And because copper sulfate has a blue color, that blue color will start to disappear, and it'll become clear as the copper ions are starting to attach themselves to the copper metal in the solution, or the copper metal that's submerged within the solution. Okay, so the previous slide we saw a very simplistic version of just explaining what the half cells look like. So now, what all needs to be incorporated? The voltaic cell needs to have proper connections in order to have proper reading and the reactions to move forward. Essentially, completing the circuit. We talked about that external wire. That means that external wire needs to be connected to each metal, and ideally, we want to have a voltmeter connected to that electrical wire so we can read how much voltage is going through this process, and we can determine how much electricity to get from that reaction, and then of course that ties to all the industrial processes that could occur. But that is just allowing a one-way circuit, and eventually that circuit's going to die because all of the anode has emptied out its electrons to the cathode. So how can we close the circuit and keep the circuit going? Well, the last piece we need is the salt bridge. This could be a glass tube if you're in a nice lab, or for us it would be absorptive paper like filter paper. So in this salt bridge, the salt bridge is going to contain or have been soaked in an aqueous solution. Typically we use sodium nitrate or potassium nitrate because they will always, our alkali metals and our nitrates always stay in solution. They will not precipitate out no matter what you react them with. In addition, sodium and potassium also have higher reactivities than most of the other metals we use, therefore always want to stay in their ion form, because the more reactive metals prefer to be oxidized and therefore in their ion form. This aqueous solution enables the negative charge to be carried in the opposite direction. So we have the electrons moving in one direction, accumulating essentially negative charge on one side. Well, this allows the ions to switch as needed. In addition, on the side donating the electrons, that side is becoming more positive, and therefore the salt bridge with its associated positive and negative ions, it can replace and move those ions as needed to keep the cells balanced. Therefore, the salt bridge helps neutralize the charge buildup in each individual half cell and helps maintain what's called the potential difference, which is what allows the reaction to continually move forward. Finally, we have essentially what a setup looks like for a voltaic cell. All right, here we have our associated half reactions. In the first cell, we have our zinc metal. Of course, this is being submerged within our zinc sulfate solution. Okay, and then on the opposite side, so we know what we're reacting it with, we have our copper metal, and that is being submerged within our copper sulfate solution. All right, so going and looking at the reactivity series, we know that zinc is a stronger reducing agent, therefore wants to be oxidized more than copper. It is going to be our anode. Therefore, it's going to carry the negative charge. That being said, what occurs at the anode is oxidation. So how does this work? Zinc wants to be oxidized. It wants to give off the electrons. So the zinc that is residing in this metal strip, what it wants to do is it wants to give off its electrons. So it's going to release its electrons, and then that species, the zinc, is going to be ionized into our zinc 2+. So now we have our oxidized species. Those electrons that were given off are now going to move up and through this external wire. It's going to move across this external wire, be read by the voltmeter, so we can see that there's a positive 1.10 volts. And that's telling us which direction it's moving in. Now, those electrons are moving towards the cathode because they are attracted to the positive end. The cathode is where reduction occurs, hence it's gaining the electrons that were released from the anode. So now this copper ion, or this copper rod, is picking up all these electrons. So now it's picking up these electrons that were moving over the course of the wire. And that is going to cause those electrons to essentially make the copper ions within that solution precipitate out and pick up those electrons. So now you get, you get pure copper coming out, and that pure copper is going to precipitate onto the metal or to the bottom of the voltaic cell. Then you have the salt bridge, which is what's going to balance everything out, because we have electrons moving up and over from our anode to our cathode. We have zinc ions that are now being shown within, or zinc ions being put into our zinc solution at a higher concentration. So now this solution is becoming more and more positive as those electrons are being lost. That being said, this copper sulfate solution is losing its positives because they are being reduced. Therefore, this salt bridge has the cation ions and the anions needed. So the cation ions are going to move towards the cathode because the solution is becoming more negative as those copper ions are being absorbed or being reduced. The anions in the salt bridge are going to move towards the anode or the oxidation state because now we have more positive charge there than there was, and those anions are going to balance out what is going on within that solution. So the different half cells make the voltaic cells with different voltages because the direction of electron flow, so that's one, and the voltage generated is determined by the difference in the reducing strength. So that's where we go back to the reactivity series. So with zinc to copper, that ratio gives us a plus 1.0 voltage. But if we were to switch to from zinc to silver, because silver is significantly lower on the reactivity series, we get a larger voltage difference. It is plus 1.56 volts. And so we're able to build batteries or voltaic cells for whatever purpose to suit the needs of how much energy we're going to need to produce in electrical form so that it is safe for the situation in which it's in. But for 9.4, you need to understand how a voltaic cell is set up. Each half cell makes a total voltaic cell. How to identify which one's going to be the anode, which one's going to be the cathode. Understanding that oxidation occurs at the anode because electrons are released. Reduction occurs at the cathode because the positive charges are lost due to the acceptance of the electrons. The voltage is the reading, is the potential difference between the oxidation and reduction states, and there's a salt bridge that will neutralize the buildup of opposite charges within the solutions themselves. And the voltage all depends on what the difference is in reactivity between the two sets of ions that are used.